So we left off with kind of finishing up some of the settings in non-adaptive experimental design, where we kind of considered at the end when we knew the Markov equivalence class to start off with. So I'll go through some kind of considerations when we're going into an adaptive setting. Also, all of this is going to be with the fixed Markov equivalence class. I think as pointed out a few times before, basically if that's kind of general, as long as you have access to a the observational version of the system is where you don't do an intervention. So this is kind of without loss of generality compared to the non-adaptive case. And I'm going to start by discussing some options that we have for greedy strategies. And I'll discuss at least why one of these, which at first glance kind of seems intuitive and like the first thing that you would want to do, can be pretty suboptimal, and then go into a different algorithm that you can actually show in a special case. So this is going to be when the essential graph is a tree. You can get within a factor of 2 from the optimal intervention in terms of the expected amount of interventions you're going to use. So that's kind of the trajectory that we're going to take from here. So I kind of divided the types of greedy strategies we might consider into 2 columns. So you might consider on the left like a worst case, where what you're trying to do is kind of greedily pick interventions. So if you take your current intervention set as this calligraphic I, then you're trying to pick an intervention that you can add to that set. I didn't write kind of the quantification over which interventions we might be choosing from, because that would vary from algorithm to algorithm or setting to setting. And you're trying to, get rid of as much uncertainty as possible. So you're trying to minimize kind of the number of undirected edges. In this case, we're going to consider the worst case over all of the graphs in the interventional Markov equivalence class. And I have some citations for papers that actually use this type of strategy where this is proposed. So one is this Hauser and Bowman paper, and then one is the paper on K-node, so bounded kind of small size interventions that I referenced earlier. In the fixed MEC, they also give the non-adaptive case. So you can also think about, instead of kind of choosing something for the worst case, choosing something for an average case, where again, we would be using something like a sampler over the uniform distribution on the interventional Markov equivalence class to compute the quantity that we're trying to minimize. This is just kind of running through some options that might come to mind. You might say, okay, well, the number of edges is only kind of one measure of the uncertainty that you have in a graph, but this doesn't actually tell you how many members are in the Markov equivalence class. So if you're thinking from a more information theoretic standpoint, you might be thinking about the entropy, like the total. If you have a uniform distribution over all of the things in your interventional Markov equivalence class, this would be log of the total number of members in that equivalence class. And here I've just neglected the log because it's a maximization, doesn't matter since that's monotonic, but I included it in the expected value case. So again, this is, I think about all of the graphs that could be in the Markov equivalence class. If that was the true graph and I did this intervention, how much do I reduce the entropy? And these 2 strategies are also explored in a previous paper. And finally, you could think about, we saw kind of the size of the largest clique was an important kind of quantity in at least the passive design case. So you could think of trying to minimize the size of that iteratively. And I'm not aware of any papers that kind of explore theoretical properties of this strategy. It's kind of high level, what our options for greedy strategies might be. You might be able to come up with kind of other ways of quantifying besides worst case or average case. And you might be able to come up with other ways of quantifying the amount of remaining uncertainty. But this would be kind of the style of a typical greedy algorithm here. Yeah, so this is just recapping the setting. We're gonna think about adaptive. We're still gonna be in the setting where we want to completely identify the graph. We have observational data, and now we are gonna have number of interventions be bounded. And in particular, I'll kind of give the argument for a case of single node interventions. So trees are really easy kind of graphs to think about in terms of Markov equivalence. So if you consider the essential graph of a Markov equivalence class being a tree, does anybody have a guess on like how many possible members of this Markov equivalence class there might be? The number of nodes, right? And the way that you can see this is, so for a DAG, you can always identify a source node. At least one node will have no edges into it. So if I pick a node as a source node, all the edges are pointing out of it. And then this is again by the Meek rule that we don't form any new V structures. We kind of propagate these edges throughout the graph. So the choice of the root node of this tree uniquely identifies the member of the Markov equivalence class. These are in like a one-to-one relationship. So you can think of finding the true DAG as equivalent to the problem of finding the root node in this tree. Okay, so there's this kind of wacky construction of a case where the what I call the information greedy strategy. So this is where you're trying to maximize the average information gain, or the average, or minimize the average amount of entropy left in your distribution, is going to be actually using an exponentially suboptimal number of interventions. In this kind of construction, you'll see we have like a 3-area tree. So it branches from the root node 3 times until at the very end, we're going to have this giant number of nodes hanging off of the bottom. So right now I'm just going to call that M. I'm going to call the thing in the bottom row, or the penultimate row, the number of nodes there, K. So does the construction make sense? Now let's consider what happens when we intervene on any node that's not in penultimate layer. So there's 1/p probability, if we're using a uniform distribution over the Markov equivalence class, that's actually the root node. If this was the root node, then because of those Meek rules, we would get all of the information about the DAG. So here I'm doing this in terms of the expected information gain. So that's where this first term, the log p over p, comes from. And in the rest of the cases, so then the root node is going to be any of the other nodes. And all I'm going to do is identify which of the subtrees it's in. So essentially, if this node is not the root node, I'll be able to identify everything downstream of it. So say I find that all of these are downstream, and this is upstream. So there will be still one big branch where the where you can't identify anything else. So you still have at least that many of the variables left. And because of the fact that all of the nodes have degree bounded by 4, I also didn't realize the slides were going to disappear when I drew stuff on the board. I don't know if that's possible to avoid. Okay. Okay, there we go. So basically, we're going to be breaking the set of p-1 nodes up into at most 4 different sets, and we're only going to be able to identify that it's in one of those other sets. So that's going to bound the number of bits that we can get from this intervention by 2. So this is roughly going to scale as 2, because that log p over p is going to go to 0 is we take p to infinity. But if we instead think of intervening on one of the nodes in the penultimate layer, we will generally get an expectation, a lot more information. And that's because if the root node is actually any of the things here at the bottom, then by intervening at this node and getting that, we've actually identified this as the root node, and then the whole graph gets oriented. And so that happens if you think of k things in the last layer, that will happen 1 over k of the time. So that's why we're going to get, you'll see the first term is 1 over k, and then you're getting log p bits of information. And here we can even just lower bound that. So p is always going to be greater than m, which is the number of things just in this subtree. And this shows that the k and the m are independent. So I can take m as large as I want. Say I may get 2 to the p squared. So this would never really happen in practice, but this is just a kind of counter example for why the information greedy strategy won't work. So we've established that the penultimate layer, those are the nodes that are going to be chosen. Now what happens is that even if the true Markov equivalence class, even if the only things were possibly the nodes in that penultimate layer being the root node, we would still only get any single one of those correct if we guessed it at random 1 over k of the time. So in expectation, it's going to take at least k over 2 interventions for us to pick out the true root node if you just imagine going from left to right. But there is an algorithm that kind of takes advantage of the fact that this is a tree, which can find the root node in, at most, logarithmic time in k. And this is basically, you can think of as like a bisection search. So the strategy is to intervene on a node where whenever we remove that node, so we'll break the tree into a bunch of separate connected components, then the largest of those remaining connected components is as small as possible. So this is somehow equal to like the minimum max entropy strategy, because we want to break it up as much as possible.
I think I missed something at the start of this.
Yeah.
So, why assume the tree structure, or is that kind of the setting we're in now? Is we're assuming this tree structure?
Yes. Yes. So this is supposing that your essential graph is a tree.
Okay.
So this is kind of a starting point for analyzing the adaptive setting and kind of thinking about the difference. So like this could have been the essential graph. And this shows that the information greedy strategy can be exponentially suboptimal for some choice of exponential.
Right. So this is a starting point to extend towards non-tree.
Yes, exactly. So yeah, this is just some kind of, here's an existence statement of this strategy takes k over 2 interventions, and there exists a strategy that takes log of k interventions. So you can show this gap, at least in one setting. Whether or not this gap is kind of a general thing, I think is an open problem. You could probably put constraints on what the essential graph is that would lead to this not being a problem. But it'd be interesting to kind of figure out what sort of constraints you need for that. So what the central node algorithm would do is kind of, if you're like staring at this, what you might intuit, that I would pick the node at the middle, at the very top. So say, at most one of these can just be pointing in, and that reduces the amount of possibilities to just the thing on the right. Then I can continue doing this. So I can do this same game for like any depth of tree. And in general, there's this nice property of trees that they always have what's called a central node in this literature, which is a node where when you remove it, all of the remaining subcomponents are at most half the size of the original tree that you started with. So essentially, this is telling you at each of the interventions that you do here, you get 1 bit of information because you're reducing the size by half. And we already said that the number of intervention or the number of possible representatives in the Markov equivalence class is P, and that can be encoded in most ceiling of log P interventions. So that's in that many bits. So that's exactly how many single node interventions we need in order to recover the tree using this strategy. That's an upper bound. And then furthermore, you can show that the expected number of interventions that would be required by this strategy is going to be at most twice the expected number that's required by any other algorithm. So this is showing somehow that trees take at most logarithmic, or at best logarithmic NP interventions to orient adaptively. And this is to kind of be compared to if you knew the graph ahead of time and you were just kind of trying to check it, then it would only require 1 intervention on the root node to verify that that was the right graph. So there's kind of a gap between these 2 settings, as you might expect. So that was pretty quick through the adaptive strategies. I could talk a little bit more about how these generalize to non-trees. It ends up becoming pretty technical. Or I could move on to some things outside of kind of what I've talked about so far, where the goal is just getting either the most information about the graph or identifying the graph in the fewest number of interventions.
I was wondering, have people either thought about or found tree use cases? Like, I know we were talking about gene networks, makes me think of cascading pathways. Have people sort of done that or thought about that?
Not to my knowledge, there's not been much on like people study like tree-based graphical models for things like phylogenetics, but not as much in the kind of like genomic, like kind of structure discovery setting. Any other questions on this style of algorithm? A lot of the papers in this space are not providing theoretical results and are kind of more showing how you might do the optimization, how these different choices perform. So as kind of more theoretically focused talk, I didn't put those in here. I'm happy to discuss maybe some of those comparisons afterwards. So we'll go into kind of the last section. I might be ending pretty early now. So
maybe before you move on. So so far we talked about minimizing or like number of interventions. I was thinking like the more social settings, if we consider other cost functions, cost functions, we probably would consider, and also having a different objective would make the optimization. Of course, it depends on function, but with these results, maybe extended if they have a different cost.
yeah, I think many of them could be. So the only thing that I'm aware of is one paper in the passive setting and some follow-up work. And what they do is they take you're allowed to assign for each node the cost of intervening on that, but then for each intervention, the cost is just the sum of intervening on all the nodes. So intervening on node 1 costs you $1, and intervening on node 2 costs you $2. Intervening on them together costs you $3. You can't kind of say, oh, it's actually harder to intervene on 2 things at the same time, so now that's going to be $5 or something like that. So the paper I'm trying to get to that mentions that is
It's okay, I can ask you later to.
This cost optimal learning of causal graphs. Questions from Zoom?
So you said that it gets a lot more technical if you go beyond trees.
Yeah.
Can you give like some ideas of what that entails?
Yeah, so I brought up the fact that you can even go back to the result right around here, that the chain components of these interventional essential graphs are chordal graphs. And one of the characterizations of chordal graphs is that they have these nice things called clique trees. So you take all of the maximal cliques. I'll actually draw something on the board here. This should be a chordal graph. Say even one node down here. Right, and the way that you construct a clique tree is you find the maximal cliques, and you make those nodes in a new tree. So here the maximal cliques would be 1, 2, 3, 4, and 3, 4, 5. And in general, you can show that there's a way to put these together so that the resulting graph over here is a tree and satisfies some certain properties. So that gets you kind of from the chordal graph space to the tree space. Now, the difficulty is that if you could imagine, okay, maybe I take the same approach of finding like a central clique in this clique tree. The difficulty is that in the case of single nodes being each of the actual nodes here, when we did an intervention, if we got an edge like this, we were able to kind of propagate all of those orientations. So the problem here is that sometimes you can propagate the orientations, and sometimes you can't. So in particular, if you label these according to what's in the intersection, then you can propagate these orientations as long as these two sets, say, are incomparable. So neither one is a subset of the other. But you cannot propagate the orientation if they are comparable. So you can prove that a version of like the clique trees, this central node algorithm works if you're in a setting where the clique tree doesn't have any of these kind of comparable labels, comparable intersections between cliques. And then you have to start defining a bunch of things to kind of handle the case where you do allow that comparability between the subsets. Great. Okay. So moving on to my last section. Going through all of these. The first thing I want to discuss is this idea of targeted experimental design. So thus far, we've been kind of arbitrarily saying our goal is to completely recover the causal structure of the system. Maybe for kind of scientific interest, we don't know how we're going to use it downstream, so we want to completely learn it so that we can kind of do anything that's possible that requires that causal model. But in general, we're actually trying to learn something for a specific purpose. So it's rarely true that kind of all of the structural information about the graph is equally important. So say in the genomic setting, we might care about identifying only a certain path, like whether or not one variable is a descendant of the other or not, or more complicated kind of quantities that are kind of purely graphical in nature, or you could even try to, so this is considered, so this is supposed to be the last section, which is where I feel like it's okay to maybe do a few shameless plugs for some of our work. So this is a strategy that also uses kind of this information greedy approach. So there are some problems with it, but basically takes the view of maximizing the information gain about the target quantity rather than about the whole graph. And this includes the whole graph being your target quantity as a special case. So you could either be trying to maximize, like in that work, we're framing it as a functional of the graph. So something that you can just look at the causal graph and tell what its value is. It might also be something that's more about kind of like functional information about how the causal system works. So for instance, you might in biology want to find an intervention that allows you to shift from one cell type to a different cell type. And if you can phrase the beginning cell type as some source distribution and the end cell type as some target distribution, you can think of finding the best intervention that gets you as close as possible to the target distribution. And that's going to be in another work that our group has done, where we consider a special case where these interventions that we're doing are a form of intervention called a shift intervention, which just adds or subtracts to the mean of a variable. And in the Gaussian case, you can show how that plays out. So I'm going to have kind of some of the, what I see as like interesting open questions in the field of experimental design throughout this last section. And this is something you could play around with a lot for different learning goals about what you actually want to figure out about your graph. How do the interventional complexity and the sample complexity change? And at least in the shift intervention work, we show that there's like an exponential gap in the number of interventions that might be required to recover just a selected piece of information versus all of the information that you want. Another point is kind of this hybrid between this single round experiment design and this multi-round experiment design. So in the single round, we said, okay, we have to decide on all of our experiments all at once, and then we observe the outcome and we don't do anything after that. And in the sequential setting, we said, I decide on one experiment, I do that, I decide on the next experiment, I do that. So you could have something in between where maybe the budget that I have to run experiments, I know here, like, okay, I'm fine with running 4 experiments, but I'm only fine with doing that in 2 batches. So I could do 3 in the first batch and 1 in the second batch, vice versa, I could split it equally. There's a lot of kind of options to the design choices to make here, and kind of figuring out what's optimal there. So again, this paper that I mentioned does this also in the batch setting, kind of using these submodular function optimization techniques that we discussed in the passive setting for optimization within the batches. And then information greedy kind of approach between batches. And as kind of a pointer to a separate literature that's considered this problem, the kind of batched bandit problem has been studied as well before. So kind of synthesizing these 2 lines of work a bit more would be an interesting direction. And one of the basic questions there is how to actually choose to optimally, not just what interventions I'm going to do, but also how do I optimally divide the number of interventions I'm going to do per batch.
Here in the first batch, we have 2 different interventions, and one of them is intervening both in blue and green intervening genes simultaneously.
Yep.
But in the second batch, you are intervening in red and green separately, but in
Yep.
the same batch.
Yep.
Why do you think we need to define these two differently?
The importance of defining intervention two at a time, like where we do both interventions at the same time versus doing one and then doing the other, but doing them in the same batch.
So in the same batch, the red one and green one,
Yeah.
you're doing them at the same time, right?
Right, but not on the same, so this is kind of what I was trying to convey with this. You wouldn't be doing it on the same kind of set of cells. So you take one set of cells and apply kind of this orange intervention and one set of cells and apply this green intervention separately. Whereas up here, this blue and green, you take one set of cells and you apply both the blue and the green intervention to them both at the same time, to that same set of cells.
I see. Got it. Oh, so the colors are corresponding to interventions, not.
Yeah.
Oh,
Yeah, so these are supposed to be like the knockouts that we're doing. Yep. Great. Okay. So now everybody was biting to ask questions about how we do things in the noisy setting. So yeah, the real world's noisy, we all know this, and how much better can we do than, I think I kind of outlined a naive strategy before of let's take some confidence level and repeat interventions until we're as sure as we want to be, and then we'll just move on. So can we do better than that? And there's at least two papers I know of kind of exploring this topic. One is, again, in this causal tree setting, where they consider binary random variables, and they use this kind of multiplicative weights algorithm. So I don't know a lot about this, but I figured some people do. So I would point to the fact that they're using, this kind of typical methodology a lot of people use in sequential decision making, and applying it to that, and showing some benefit. And then there's also kind of from a different angle, rather than trying to completely discover the causal graph, there's this paper that studies a kind of goodness of fit testing problem where they posit a graph along with a distribution. So this is all in the discrete setting. So they posit a bunch of essentially conditional probability distributions where the whole distribution factor is according to the graph. And then you try to probe a system in the real world about essentially whether or not your kind of graphical model and equations that you've written down are a good description of that system. And the example that they give is if, in software, you design a circuit and you expect it to perform a certain way, and then you go and actually implement it in hardware, how do you kind of minimally choose interventions that allow you to test whether your software model that you expect to be implemented is actually kind of realized in this hardware model. And this paper studies a few other problems in this setting. So I think somebody asked a question earlier about how to pick interventions to actually kind of learn the equations in a model. So they also do that, but all this is going to be more in a kind of, I have a fixed graph that I'm being given, and either I'm trying to learn the equations for it, I'm trying to test if the model that I have is a good one for the data. So I have that written out here. A bit more of the formalization of that. So I'll pause on this slide, and if anybody wants to ask questions about dealing with noisy data and interventions.
That's another question. Just a few minutes ago, you mentioned, you gave an example about learning, I think it was learning running a set of interventions to shift like a cell from one
Yeah.
to another, right?
Yeah.
That was under, I think, the heading of targeted experimental design, right?
Yeah.
So I'm just I'm thinking about that because I'm not sure I see the example like in full clarity.
Yeah.
You're trying to learn a set of interventions to do what exactly, like how does the graph correspond to this example of like shifting a cell from one type to another? You know what I mean?
Yeah. So
I'm not sure how the causal discovery, like where the causal discovery part comes in. Or...
That's a great question. So doing this kind of on the fly, that assume that like the true causal graph. So the assumption that we're making here is that you, again, you won't be starting with this data, but there will be a true causal graph, and the difference between kind of your original causal graph, so you could say this is the observational one, and your target system is going to be, so imagine this is a linear structural equation model, so each of these will get some edge weight, and each value will be the edge weight times its parent, some like mean zero noise. So what we're assuming is that the target distribution, so these variables are going, these A's are going to induce some observational distribution over your model,
like over the axis.
over the axis. And then we assume that the target is generated by performing shift interventions at some set of nodes. And the shift intervention is something that says, okay, I'm changing your equation so that instead of saying x2 is equal to like a1 to x1 plus whatever noise that you have here, it's going to be replaced with, you still have the same dependence on your parent, but there's this additional bias term. So it's going to push you up or down by, in this case, B2. So we assume that like what's actually going on in the real world, this is the difference between the two distributions. And the goal is to find the set of nodes along with the weights that get you from one to the other. And without knowing what this causal model is, so if I just write down x1, x2, x3, x4, x5, and so on, especially if I have more edges and stuff, then you can't just look at the beginning distribution and the end distribution and immediately identify what intervention happens. So you have to know a little bit more, like you could do this if you knew the causal model. You can just look at the beginning and end distribution and just write down where all the shifts are happening. So there's this kind of interplay between your uncertainty about the causal model and what you're actually trying to learn, just this intervention. And that, again, is in the noiseless setting. All right, so the two things that I kind of laid out at the very beginning of the talk is that we're going to focus on a noiseless setting and that we're going to focus on causally sufficient. So what do we do if the system actually isn't causally sufficient? And so there are some latent confounders, some things that we don't observe that enter into the structural equations. And we actually have a null result here that you can't always identify the true causal graph just from single node interventions if you have these latent confounders. So we can determine this by comparing these two graphs. So the only difference here is that there's no edge between x1 and x3 in the second graph. Everything else is the same. But any single node intervention that we do, if we think of cutting out x1, So performing a do intervention on X1. Then I'll just write down all of these models. We have more than enough time. Right, so if we perform a do operation on X1, we will cut off this edge, but that doesn't give us any new conditional independencies. So we still have, and this will happen in both graphs. So even if we were in this graph where we didn't have the edge between X1 and X3, can I still see that on Zoom as long as I don't go any lower? Okay. Right, so in both of these, X1 and X3 are dependent, like marginally, if we don't condition on anything. They're also dependent if we condition on X2, which is the only other thing that we can condition on. And then we can check all of the things that we could possibly remove. So if we did an intervention on X2, what would happen in these two graphs? So again, X1 and X3 are going to be dependent in both of these graphs. There's no extra information that we can get about whether that or not that edge is there. And then finally, if we intervene on X3, both of the graphs, in both cases, it's still going to be dependent on X1 because of this. So there's no way to tell whether or not there's actually this edge between X1 and X3 just by using single node interventions because of the way that it's covered up by this L1. Yes, I messed this up. That would be the graph after. So these are even actually the same graph there, not just the same d-separations on observed variables. Another way to see this would be kind of using the mag stuff that we used the other day and think about when we delete all of these interventions, whether the resulting mags are Markov equivalent. So that's our null result, but there is hope. So if we allow for interventions of any size, at least in this graph, you can show if I delete the edges into X1 and X2, I'll be able to render things independent. So I have X1 say, I think it was the intervention on X1 and X2 that allows you to distinguish between these. So you just have still your edges into X3, right? In both of these graphs. But now X3 is going to be independent of X1 and X2, whereas in this one, it still depends on X1.
X2 to X3.
Yes, thanks. And yeah, so this is a general result, also in Frederick's PhD thesis. And one of the open questions would be, if we actually bound the number of interventions by k, what are conditions on the graph that make it identifiable, or the graph and the latent variables and so on that make it identifiable from interventions whose number of targets are bounded by at most k. Y'all have anticipated a lot of the kind of things that I have shown. So I'm glad I was getting very good questions. I think somebody earlier asked about basically, so I was giving these kind of worst case bounds. What happens? Yeah.
Go one back to that question. So is it maybe, I mean, is one direction clear that like if you have latent variables that point to K, then obviously you need at least interventions of size K, I guess. Is that correct, Chandler?
Yes, the question was if we have latent variables that point to K nodes, if we need interventions of at least up to size K in front of it. Yes.
Right. So that was kind of in the previous example because you had the latent node that points to.
Yeah, so we have at least two, yeah, interventions. Okay, so now we're moving on to this question of kind of lower bounds that just depend on either the graph itself or something like the Markov equivalence class. So how good can we hope to do in the best case instead of the worst case? And this is kind of the setup that I described earlier, just a bit more whimsical, but your friend comes up and tells you that the true graph for a causal system is this G star, but you don't completely trust them. So you want to check this out yourself, but you don't want to waste your time. You're going to use a minimal number of interventions. In this case, all you have access to, say, are single node interventions. So we already discussed in the case of a tree, you can do this by only intervening on one node at the root. In the case of a clique, on the other hand, you basically have to kind of intervene on every other node. So if they tell you that the clique is of the form 1, 2, 3, 4, 5, so it would have all of these edges. Basically, to correctly subject everything to an orientation test, you would have to kind of go and intervene on every other node. So in this case, it would take 2 interventions. So from here, you'd be able to learn all of the edges going into 4 and out of 4. And from here, you'd be able to learn all the edges going into 2 and out of 2. And then you'd basically be able to orient these other edges by Meek rules. So you have 2 to 3, you can't go back. And same here, 2 to 5, you can't go back. And that's going to be the minimal number so that you can at least guarantee that you will orient the edge between every pair. And then we have a work that shows that you can find a set of minimal size, basically using the same property of kind of taking the chordal graph and thinking about the clique tree and then thinking about kind of directed versions of the clique tree. And all of those things, because there are these nice graphical operations on chordal graphs, are linear or like low polynomial time. So you can just run this algorithm and in this setting, find the intervention that you would do that minimizes the number of nodes that you would want to use. However, this is not necessarily going to be the same number of interventions or the same set of interventions for every DAG in a Markov equivalence class. And this is an example of 2 DAGs that would require different sets and even different numbers of interventions. So you can tell these DAGs have the same adjacencies and they both have no unshielded colliders. So they're in the same Markov equivalence class. However, for the graph on the left, the smallest size intervention, or like 2 single node interventions that you would need to do would be 1 intervention on this x2 and 1 intervention on this x3 versus the one on the right, you can get by with just an intervention on x2. So it's kind of easier to see for the one on the right. You get all of the edges around x2, and then you get the edge from x3 to x4 from acyclicity. For the one on the left, it's easy to see that you get all of the edges, but then you have to check each of the single node interventions and see that all of those would leave at least one of these edges unoriented. So in general, if you want to do something that is kind of universal and like does everything, like lower bounds everything in the Markov equivalence class, we kind of gave a weak thing there that's based on kind of summing up the sizes of the cliques, or really cliques minus all of the cliques that kind of come before in the clique tree construction that we give. And then there's a recent paper that gives a tighter bound and shows, shows that this is like almost an optimal bound. This is the better bound you can get is like a factor of 2.
Quick question on the previous slide, the results are for causally sufficient systems.
Yes. Yeah, sorry, I'm kind of bouncing back and forth. These were the only 2 slides on that insufficient. Yeah. So I will give us back the final hour. Yeah, not think I would go that fast to this, but
Thank you.
thank you all. Yeah.
Any more questions? Actually, I just had a little one. This graph you said,
Yeah.
it's just a small thing. It said intervening on 4, we figure out those those 3 edges that we gave.
Yeah.
I think I'm just missing something there. How do we? Is that like by some? A priori?
This is so we're only intervening on 4, and you're always able to find out the parents and children of the thing that you intervene on, because there's 2 ways to think about it. First, they're adjacent already, so this is assuming the Markov equivalence class to start off with. And then by the fact that I intervene on this variable, but these don't change, that implies it's upstream, and that the fact that this one does change, it's downstream. The other way to see it is through kind of just adding in this intervention variable and then thinking in terms of the B structures.
So yeah, that part I get, but like the a priori kind of assumption, it's in this case, like you said, we're assuming we know the equivalence class.
Yes.
This is like I think this is a complete graph. Like
this is a complete graph. Yeah.
And that's in this example, that's particular to this example. We're assuming like we know a priori this is a complete graph.
Yeah. So the setup that I was kind of considering, maybe you trust your friend to tell you the correct Markov equivalence class. Do you already have enough observational data maybe to verify the Markov equivalence class yourself?
I see.
Yeah.
Okay, yeah.
The question one is like, say my objective is to maximize the value of the node.
Mhm.
If you do the problem as say vanilla modular value, then you need to mention the NAR. Does it help to learn the structure on the way? Include say recurrent or something.
I'm not as sure about the literature on combining kind of the bandit kind of, I want to maximize the outcome of a particular node with an unknown causal structure. You're actually working on something like that. Do you have an answer to this question?
I would say that like it's not very well.
Yeah. So if you knew the causal graph, like definitely knowing the causal graph can help you determine which sequence of arms that you want to pull. But if you don't know the causal graph, it's definitely a harder problem. It's pretty open.
The other question is, all the node results like missing a net that's already there versus a net that's really there.
Yeah.
There's no distinction. Like it could be like a fake, very vague infinitesimal correlation, and the mistake is the same.
Yeah.
Very strong correlation.
Yeah.
So isn't that problematic? It couldn't, maybe I miss an important edge versus missing a non-important edge.
Yeah, that's a really good point. So basically, the point it's making is that kind of our false negatives of whether or not an edge is there might differ a lot based on like how much it affects our predictions or something, based on whether or not that's kind of a strong edge or like a very weak edge that could almost be just gotten rid of and give you the same causal model. So yeah, that's definitely a problem with like these kinds of analyses. And when you do put things in finite sample settings, usually in order to get these results, the two papers that I cited will put lower bounds on kind of the strength of the edge, so that you kind of don't run into that. But you could probably also do something where instead of forcing everything to be lower bounded, you could just change kind of your evaluation criterion to take into account how strong the edges are.
I just wonder, can I comment on the situations with cycles?
I don't know anything about the situations with cycles. I don't actually even, not completely sure if it's been studied or not. I haven't noticed the papers at least.
So for the last problem of verifying that,
Yeah.
that was for atomic interventions, right?
Yes.
For
It gets, so he is pointing out that this is for single node interventions, which are also called atomic interventions in the literature. Yeah, I certainly like the proof strategy we use doesn't extend to that. I haven't seen people do anything with interventions that contain more than one node. And kind of, this goes back to some of the points about how submodularity and these other properties break down. So I think I would take the stuff from the results from single node interventions a little bit with a grain of salt, because there's potential that you can't get the same types of results, or the results kind of qualitatively change in the multiple node settings.
So in a causally insufficient system, so if I, let's say I design the perfect experiment that I think will work.
Yeah.
But is it possible that if I do some intervention and then I kind of find that, oh, there's a latent variable that I kind of did not think about? Oh, that's something. So like you have a graph that you think it's complete, but like you're not sure about whether it's complete. So like with this type of intervention study, is it possible that you're able to detect where the latent variable is?
I believe the answer is yes. Most of the when you do the interventions, that will reveal more information about where the latent variables are, but I'm not the doctor. Yeah.
Just a question from Zoom. Is there a reference to a real life application using successfully these methods?
No.
I was thinking that one of the things that is the Sachs et al. Data has been studied quite a bit in actually several people have studied it, and I think the latest was Joris Mooy's group actually reanalyzed it and looked at the sequences of experiments and stitched together the graphs from those experiments. So that's one example, and then the other that comes to mind is the Steakhoven et al. Paper on the flowering patterns of Arabidopsis thaliana. I think that also had various interventional components where that was stitched together.
But a lot of these are like retrospective, right? Of this data set was already gathered, and then we look at picking the interventions. I haven't seen this used in kind of a prospective setting where you've convinced some biologist to actually use your intervention design strategy.
And just on the cycles, I was going to say, so on the cycles, it depends, of course, how you think about what you mean by a cyclic graph, but at least let's go with the linear cyclic model, like really linear Gaussian cyclic model for the system, for which is perhaps the best understood cyclic causal system. There are identifiability results of sequencing the experiments, or what combinations of experiments you need to identify that's work by Anti-Utu and JMR. Other question here from, is there a difference in these interventional results between parametric and non-parametric models, especially in the causally insufficient settings?
I want to say yes. For instance, even the definition of the interventional Markov equivalence class can change. So in the setting with shift interventions, if you say I shift both of these values by some known amount, and my intervention consists of intervening on both of these. Usually, what I would say with these do interventions is that if you have an intervention that, I don't really know how to represent this graphically, but if you had an intervention that simultaneously intervenes on both of these, you wouldn't learn any information about X1, X2. Here, you would learn information. Actually, you would learn the graph. So you would learn both that they are connected because X2 would still depend on X1, but also you'd be able to say, oh, well, I guess you would need observational data. So usually from observational data, you would have this undirected, and then if you did this type of intervention, you wouldn't gain any orientation information. But here, you can see that X1 actually is the thing that's shifted by B1, but then X2 in general is not going to be shifted by exactly B2. So there's a way to tell these apart by incorporating kind of additional information about what the interventions you're doing is.
I think the question might be not about the weak or strong interventions, but about whether there's a parametric assumption about the
causal model. Yeah.
So say linearity or something like that versus just a completely non-parametric setting.
Right. That I'm not aware of differences.
Yeah, so
between,
I think
especially
linear case. So if we have a confounded system that is linear Gaussian, then we can even do single identifiability with single interventions, which we can't do with the complete non-terminative.
Right. Got it.
At least this is how I understood the question.
Yeah. Also, in like the other kind of hour, I don't have any more, but I'm happy to kind of walk through like maybe particular questions. But I don't expect everybody to kind of come back here and watch us kind of stumble through stuff. It's like what's prepared.
Okay, let's first thank Chandler. Also, thank you to both to Spencer, Daniel, and Thomas as well, and Chandler for taking this on for the bootcamp. It's an enormous amount of work to put this sort of day together for everyone, and they were willing to do that. So please join me in thanking all four of them again for doing this, because I know it's a ton of work to do that sort of thing. So thank you all for coffee outside, and then we're not going to have the last hour in any formal way. So if you want to come back and talk about things, we'll be around, but there won't be any sort of formal. And then next week, remember, it's the boot camp for the other program. There's, I think, Basil will be running that show. Then we don't have any kind of fixed events for the causality program, but of course. I think many of us will be around. Some of us will perhaps attend the other boot camp, and then we'll start up discussions independently of the formal events next week. And then more official events for the causality program will then kick in again the week after that. Okay. Anyway. Thank you all for coming. Enjoy the coffee.